Today's problem involves a conical surface and finding potential differences in between points on the surface of a conical surface. So let's read the question. We have a conical surface, an empty ice cream cone carrying a uniform surface charge, sigma. The height of the cone is h, which means this height over here, this is h, and the radius of the top is h. Find the potential difference between the points A and B being over here and A being over here. All right, so let's approach this problem. Oh, by the way, this problem is taken from the 4th edition of David Griffiths, a book on Introduction to Electrodynamics. All right, so let's jot down the information that we have. We have the surface charge density, which is sigma, and we know that sigma is equal to dq dA, and we basically have to find out what V, the potential difference between point VB and VA is. This is our goal. All right, so to find out the potential differences, let's first find out what the potential is in those particular points, which is point B and point A. So I'm going to start off with finding what the potential is at point A first. All right, so we're going to use the equation V sub R. Oh, I should be clear. We are going to find the potential at point A first. Find VA. All right, so the formula that we're going to use over here is that V sub R, V of R is 1 over 4 pi epsilon naught, the integral of sigma all over the displacement vector times dA. Now let's be clear with what this displacement vector is. So the displacement vector is a vector pointing from any infinitesimal charge dq to the point where we're interested in finding the electric field. All right, so in this case for point A, let's say we have this patch over here that has a charge dq. All right, so in this case your displacement vector is r minus r hat. All right, the vector r minus r hat. Now r is the vector that points to the point that you are interested in finding the electric field at, which is in this case just A. All right, and I'm gonna set my origin to be at point A. So this is where my origin is. Okay, so in this case r hat is basically what? 0, right? Because I am situated at the origin, and now my r prime vector points to my dq. It points to the direction where my infinitesimal charge is. So we basically have to find out what r prime is in this case. Okay, what is r prime? Well, in this case, I'm going to use cylindrical coordinates to find out what my r prime is. Okay, so in cylindrical coordinates, notice that my r prime is situated at a height z and a radius s away from my origin. All right, so basically my r prime, this should be r, and my r prime is basically z hat plus s hat. I'm going to use s hat as Griffiths uses in his textbook for denoting conical coordinate systems. Okay, so plugging these things into here, we get that the displacement vector is basically what? Negative z hat minus s hat. All right, okay, so basically we have that this is my displacement vector r, and we are interested in finding what the magnitude of the displacement vector is. So we have that the magnitude is equal to z squared plus s squared raised to the power 1/2. Okay, now for dA. Okay, I'm just going to denote dA as dA prime because this denotes to any arbitrary point. Same thing, as dA, whatever you think. Okay, so as for dA refers to any infinitesimal patch, okay, on the surface. Okay, so the dA is basically the infinitesimal patch of surface where your charge dq is at. Okay, so let's think about what dA really is. So dA is the radially outward curve, okay, the radially outward curve over here, which is basically s d phi or s d theta. I'm going to use theta over here as my azimuthal angle times the distance that this takes while going down. Okay, so this is just, focus on over here, so this is just this distance over here. So the patch that you're creating is kind of like this, so you go radially outwards and then you go down. Okay, so it's this distance over here. So let's think about what this distance really is. So over here, if you draw the triangle, we are trying to find out what this distance is, right? You go dz prime up in this way and ds prime radially outwards, right? So this distance over here is basically dz squared plus ds squared raised to the power 1/2. Okay, now as you can see over here, this triangle over here, formed over here, is similar to this triangle that's formed over here. I'm referring to this triangle, which is basically the same as this one. Okay, so this triangle has ratios like this, and the triangle with the infinitesimals is basically like this. And as you can tell, for any point along the cone, dz will be equal to ds for these two triangles to be similar. All right, so plugging this relation over here, we get that the distance is basically 2ds squared raised to the power 1/2. And I'm going to use the prime notation, of course, and this just basically gives you the square root of ds prime. Okay, so plugging it over here gives you square root of ds prime and theta prime as well, a prime as well. Okay, and I can write this down as dA prime is equal to the square root of ds prime d theta prime. Oh, I'm missing an s over here. ds prime d theta prime. Okay, so plugging this value into my equation over here, we get that v sub r is equal to 1/4 pi epsilon naught times the integral of sigma all over the displacement vector's magnitude times dA prime, and I'm going to write this down as k. All right, so you have a k times sigma over whatever. So you have sigma, this displacement vector's value is what, let's see, it's this z squared plus s squared. Okay, z squared plus s squared raised to the power 1/2. Okay, and then there's dA prime, which is square root of s ds d theta. Okay, now as you could tell, at any point z is equal to s from this triangle over here, right? So z is equal to s, and I can simplify my things by writing this down as I can bring the square root of 2 outside. So you have s ds prime d theta prime all over square root of 2 s squared. The square root of s squared is basically s, so I can write it down as s. I'm going to write this down as s primes because I'm referring to any arbitrary point, s primes and z primes. This should be primes as well. Anyway, so now we have that, and as you can tell, the s's cancel out. I should have a k over here. The square roots of 2's cancel out, and then you have k times the integral of ds d theta, and this should be a double integral actually. Okay, now for the bounds. So for the theta, it should go from 0 to 2 pi, and for s, it basically should go from 0 to h, because as you can see, S ranges from the origin over here, which is at 0, to this point over here, which is at h. All right, so this ranges from 0 to h, and this integral isn't quite difficult to solve. So you end up getting that this is k times 2 pi, and then you have h. So basically you have that your v at point A is basically k 2 pi h. Oh, I think I've dropped my sigma somewhere, so the sigma over here, so the sigma should come outside as well. So this is sigma, and this should be sigma. All right, and you can write this down in other ways if you like, but I like this form. Okay. All right. Okay, so this is my V at position A. Oh, one other way of writing down VA is that this is sigma h all over 2 epsilon. And this can be found by plugging in the value of k is equal to 1 over 4 pi epsilon over here. Okay, now for point B. Okay, so for point B, everything should be the same except for the fact that your displacement vector is now different. So let's think of how the displacement vector would look like in this case. So you have your cone, just as in the previous case. You have your cone, and if you set your origin to be over here again, this is point A, this is point B. This is the place where you have dq now, right? But your position vector, your displacement vector would point from dq to this point over here. So this is your position vector, and this is your r prime vector, and this is your r vector. Okay. Now as you can tell, your position vector is basically r minus r prime. Now r is basically the height times z prime, right? Because this is the height, minus r prime hat. Yeah, there should be a prime, so it's r prime, and this is basically the same as before, right? So this was z hat plus s hat, and you can simplify this to look like h minus z whole squared plus, oh, no squares, sorry, h minus z hat plus s prime. Okay, and you can find out the magnitude to be equal to h minus z whole squared plus s squared raised to the power 1/2. Now, as you can tell already from our previous geometrical relations, that for any point z prime, I should use primes over here, mess up with the primes. Yeah, for any point z prime, you have that z prime is equal to s prime because of the geometry of the similar triangles that we are using. So by using that, we can write this expression down as h squared minus 2hz prime plus z prime squared plus s prime squared raised to the power 1/2. And you know that z prime is equal to s prime, so you can basically write this down as h squared minus 2h s prime plus 2s prime squared raised to the power 1/2. Okay, so now we're ready to find out what VB is. So VB is, of course, k times sigma all over the displacement vector's magnitude times dA prime. Okay, so k stays over here. We have the sigma is a constant. You can pull it outside, and we know what dA is, which is the square root of 2s prime ds prime d theta prime all over sigma, the displacement vector, whose magnitude is h squared minus 2hs prime plus 2s squared raised to the power 1/2 from here. Okay, now this integral has this is a double integral, so I can write this down as square root of 2 s prime ds prime d theta prime all over h squared minus 2h s prime plus 2s prime squared raised to the power 1/2. Now for the theta part, it goes from 0 to 2 pi, and for the s part, it goes from 0 to h, right? Just like in the previous case. Now this is an integral for the computer to solve, but I will plug these things into the computer and just give you the result. And the result, you can try it out on your own as well. It just gives you pi sigma kh log square root of 2 plus 1 all over square root of 2 minus 1. And this is v at point B. Okay, and you can write this down in other terms as well if you want. But finally, if you want to find out what the potential difference VB minus VA or VA minus VB is, you get that VA minus VB is basically pi sigma kh times 2 minus log square root of 2 plus 1 square root of 2 minus 1. And this is the potential difference across the 2 points. So that's all.